Alright, what's up guys? Here we are with PreCalc section 9.7. Plan on being gone for this one, so here's a video for it, just in case. Probability. Okay, we're going to be finding probabilities of events, find the probabilities of mutually exclusive events, find the probabilities of independent events, and find the probability of the complement of an event. Alright, so let's flip it over here. Any happening for which the result is uncertain is called an experiment. The possible results of the experiment are outcomes. The set of all possible outcomes of the experiment is the sample space of the experiment, and any subcollection of a sample space is an event. Lots of math words there. All those bolded words should be in your book if you need any further detail with those. The probability of an event. For instance, when a six-sided die is tossed, the sample space can be represented by the numbers 1 through 6. For this experiment, each of the outcomes is equally likely. Okay? 1, 2, 3, 4, 5, 6 is all have the same chance of coming up. To describe sample spaces in such a way that each outcome is equally likely, you must sometimes distinguish between or among various outcomes in ways that appear artificial. Get to the good stuff eventually, guys. A lot of vocabulary here first. Oh, we did the same thing over. This got stuck. Alright, what is the sample space for each of the following? A letter chosen randomly from the alphabet. So there's 26 letters, but what are those letters? Our sample space. Okay, we got all the letters. A, B, C, ... X, Y, Z. Okay? Close your set. Six-sided die. Sample space. We got 1, 2, 3, 4, 5, 6. A coin is flipped once, and a six-sided die is also tossed once. What are your possibilities? What's our sample space? Okay, we could have a heads and a 1. You could have tails and a 1. You could have heads and a 2. You could have tails and a 2. ... Heads and a 6, tails and a 6. Okay, those are all our possibilities there. Alright, so here's the book definition for probability. If an event E has n of E equally likely outcomes, and its sample space S has n of S equally likely outcomes, the probability is n of E over n of S. Okay? Successes, sometimes you see this as success over total possibilities, or what you want divided by total possibilities. Okay, I think either one of those other ones would make a little bit more sense maybe than what is written there. Okay, the probability of an event is between 0 and 1. 0, if it is exactly 0.0, that means it's impossible, cannot happen. 1.0 would mean it's certain to happen. It 100% definitely will happen. It's going to happen. Okay? 0.5, 50-50, equally likely to happen and not happen. 0, we said, is an impossible event. 1 is a certain event. It will happen. Okay, if you were in class when we first discussed this, this is about as far as we got, I think. 2 coins are tossed. What is the probability that both land heads? So heads is one option. Okay, first coin could be heads and second coin could be tails. We could go tails heads, or we could go tails tails. So we got 1, 2, 3, 4 outcomes, and the only one we're interested in is heads. So that's 1 out of 4. A card is drawn from a standard deck of playing cards, probably that it is an ace. So we talked about that. Standard deck of playing cards is going to have 52 cards. 4 suits, 13 cards in a suit, 4 times 13, 52 cards. Probability that we draw an ace. So we have ace of hearts, ace of diamonds, ace of clubs, ace of spades. There's 4 aces out of 52 cards in a deck, 1/13. And a 6-sided die is tossed twice. What is the probability that the total of the 2 tosses is 5? Okay. Well, I'm not going to redraw this chart. I'm just going to cheat and give you this one. Okay. So, we're throwing 2 dice. Okay. Each one is a 1 through 6, 1 through 6, and we add it up. So if we got a 1 with a 1, and we get a 2. 2 and a 1, my total is 3. 3 and a 1, my total is 4. Okay. You keep filling in your chart. 6 by 6 means that there's 36 total possible outcomes. And I see 1, 2, 3, 4 possible ways to get a 5. We can go 1, 4, 2, 3, 3, 2, 4, 1. Those are 4 ways that we can get a total of a 5. So 4 out of 36 total ways would reduce to 1/9. Okay. A class is given a list of 20 study problems, from which 10 will be part of an upcoming exam. If a given student knows how to solve 17 of those problems, find the probability they will be able to answer all 10 questions on the exam. Okay, so success over total. All right, the student knows 17 of them. All right, and there's going to be 10 of them on the test. So, combinations, because order doesn't matter which order they are on the test, as long as these questions are on the test. So there's 17 that the student knows how to do, picking 10. What's the probability that those are the same as the 20 picking 10? Okay, so there are 19,448 different combinations of the 17 problems that the student knows. Okay, and then just adding those 3 extra problems, number 18, 19, and 20, those last 3 that the student does not know how to do. So 20 problems picking 10. There are 184,756 total different arrangements for those. So if you know how to do 17 out of the 20, and they're picking 10 to be randomly on the test, you'd have about a 10%, 11% chance of getting it perfect. Crazy, just those 3 extra problems, what that will do. All right. A college sends a survey to selected members of the class of 2009. Of the 1,354 people that graduated that year, 672 are female and 682 are male. If a graduate is selected at random, what is the probability that person is female? So we're talking about females, 672, divided by the total number of people that graduated in that class, 1,354. And we're looking at 49.6% chance of that a randomly selected graduate from that year would be female. Mutually exclusive events. 2 events A and B from the same sample space are mutually exclusive if A and B have no outcomes in common. Okay, kind of like flipping the coin and rolling a die. In the terminology of sets, the intersection of A and B would be the empty set. There's no intersection of the 2 sets. There's no overlap. For instance, if 2 die are tossed, the event A of rolling a total of 6 and the event B rolling a total of 9 are mutually exclusive. One does not necessarily depend upon the other. My odds of rolling a 9 do not depend on the odds of rolling a 6. Okay? If there is an overlap, to find the probability that one or the other 2 of mutually exclusive events will occur, you can add their individual probabilities. Okay, so if there's no overlap, you can just add your probabilities together. If there is an overlap, okay, probability A plus probability B minus the little piece of overlap there. All right, so that's kind of tricky. We're going to do an example just like that right now so you can see what we mean. So back to that 52 card deck. What's the probability that the card is either a club or an ace? All right, so clubs, there are 13 cards per suit. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. So ace would be like a 1, so 1 through 10. Jack, queen, king. There's your 13. So we got 13 out of the 52 cards are clubs. All right, or an ace. We know there are 4 aces. I think we had that problem just a little bit ago. Okay. But we have overlap. We have overlap because we have an ace of clubs. So we got one card that's being counted twice. So we have to subtract 1. Okay. So that would be a total of 17 minus 1, 16 out of 52, or 4 out of 13. Okay, so we had 13 out of 52 cards are clubs. 4 out of 52 cards are aces. Okay, subtract the overlap, because that's kind of like counting it twice. The ace got counted twice, so by subtracting 1, you're kind of taking it out of one of the 2 groups. You're only counting it once then. So 16 out of 52, and reduce, if possible, 4/13. All right, we got a chart here. Personnel department of a company has compiled data on the number of employees who have been with the company for various number of years, blah, 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 blah. All right, let's zoom in a little bit so you can maybe see those. What's the probability that an employee chosen at random has been with the company for 4 or fewer years? So 0 to 4, 157 out of, if you add all these up, I'll do the work for you here, I think it's 529 total employees. Okay, so for A, 157 out of 529. Okay, B, 9 or fewer years of service. So now we're going to add those 89 plus the 157. All right, there's no overlap. It's 0 to 4, and then the next section is 5 to 9. There's no overlap between those, so there shouldn't be any overlap of employees, so we don't have to subtract any. It's just as easy as adding them together. 157 over 529 plus 89 out of 529 for a total probability of 246 out of 529. Okay, there was no overlap, so I didn't have to subtract anything away. Independent events. 2 events are independent if the occurrence of one has no effect on the occurrence of the other. For instance, rolling a total of 12 with 2 6-sided dice has no effect on the outcome of the future rolls of the dice. To find the probability that 2 independent events will occur, you get to multiply their probabilities of each event. All right, so flipping a coin is 50-50. Rolling at 1 dice, 1 die is 1 out of 6. So any combination of head, tail, and 1, 2, 3, 4, 5, 6, you'd have 2 times 6. You have 12 possibilities, 1/12. That's how you can do that. A random number generator selects 3 integers, 1 through 20. What's the probability that all 3 numbers are less than or equal to 5? So 1, 2, 3, 4, 5. So that's 5 numbers that would satisfy less than or equal to 5 out of our total of 20 numbers. So the first spot, 5 out of 20 is 1/4. Second spot, it's those same 5 numbers, 1/4, and the third spot, 1/4. Okay? So the probability of getting a number that's less than or equal to 5 in the first spot is 1/4. Same thing for the second spot, same thing for the third spot. It's a random number generator. It could give you the same number back to back, so that's why we can still count all of them. So 1/4 times 1/4 times 1/4, the probability of all 3 of them being less than or equal to 5, 1/64. Okay, and the last little thing here we're going to look at is the complement of an event. The complement of an event, A, is the collection of all the outcomes in the sample space that are not A. Okay, denoted by A prime. Because the probability of A or A prime of one or the other happening is equal to 1, they're mutually exclusive. And so that it would follow that adding those two together would those would be everything possible. All right, so rolling a 6 or everything else that's not a 6. 1, 2, 3, 4, 5. Well, rolling a 6, probability of rolling a 6 plus the probability of rolling everything else that's not a 6, 1, 2, 3, 4, 5, that's going to take care of everything. So that's going to equal 1. So you can rearrange that. The probability of A prime, or the complement happening, is 1 minus the probability of A. Sometimes that's easier to do than going through and calculating the actual probability. Okay, probability of winning a certain game is 1/4. So opposite of winning would be losing. What's the probability of losing the game? Well, everything that's not winning. So 1 minus the probability of winning would give you your probability of losing, 3/4. Okay. Application problem. A manufacturer determines that a machine averages 1 faulty unit for every 1,000 units it produces. What is the probability that an order of 200 units will have 1 or more faulty units? Okay, so the probability of being faulty or having a bad unit is 1 in 1,000.
Alex, staff now, please go to Ms. Mullman's room. Alex, staff now, please go to Ms. Mullman's room.
Sorry about that. So let's go with the complement then of not being faulty or being a good part there that they're making would be 1 minus that. So 1 minus that is going to be 999 out of 1,000 are good. Okay? So we want to know what's the probability that an order of 200 units will have 1 or more faulty units. Okay, so faulty units, that's going to be really, really small. It's going to be kind of tough to do. So let's go the other route. We're going to go, so we're trying to find probability of 1 plus faulty units out of an order of 200. That would be equal to 1 minus the probability of getting all good units. So we're going to find the probability of getting all the good units and then subtract away. Because 1 plus faulty, you're going to have to find the probability of 1. Then have to find the probability of having 2. And then find the probability of having 3. And then add all those up. That's going to be quite a lengthy process. So much easier to just calculate one thing. The probability of all of them being good. Alright? So the probability of all of them being good, each individual part is a 999 out of 1,000 chance. We have 200 parts. So times 200, times itself 200 times, or to the 200th power. That is the probability of all 200 being quote-unquote good. Okay? So 1 minus that, okay? So this is all of them being good. If I take that away, what's left? Then at least 1 is faulty, if not more than 1. So if I take the total probability, 1 minus the probability of all of them being perfect is going to leave me with the probability that at least one of them is not perfect. So we have 999 divided by 1,000, 0.999, kind of brain dead on that one, to the 200th power, 1 minus, all right, and our probability that one or more is faulty, we're going to have 0.181. Okay, even with the probability of 999 over 1,000, when you have 200 of them, your probability of being all of them perfect is only 0.818. Okay? So I subtract out the probability of all of them being perfect. What's left? Something's not perfect. Either one of them or two of them or three of them is not perfect. 0.181. All right? There you guys go. You should be good for section 7 on probability. The plan tomorrow is to have a review day and then test day on Friday.